Hello learners, within this small lecture, I'll be discussing about the Nyquist stability criteria that is used to ascertain the closed loop stability of the system. What is Nyquist stability criteria? It is a stability test for the time invariant systems in the frequency domain. It is based on the complex analysis result known as Cauchy's principle of argument. And its importance lies in the fact that it can also be used to determine the relative degree of system stability by producing the so-called phase and gain stability margins. These stability margins are needed for frequency domain controller design techniques. This is the Nyquist plot. So whenever we are using the Nyquist stability criteria, we should first of all understand what is a Nyquist plot. Nyquist plot is basically a Nyquist contour. So first of all, we have to consider the Nyquist contour. So Nyquist plot is basically the polar plot of the function 1 plus GSHS when S travels around the contours given in this figure. This is the contour in the S plane. This is called Nyquist contour. This contour covers the whole unstable half plane of the complex S plane. So this is S plane. This is real part of the S sigma. This is J omega. And if we know that this portion relates to the unstable portion, and this is the stable portion. In case roots of the characteristic equation are lying in the left half of the S plane, the system is stable. In case any one of the root of the characteristic equation is lying in the right half of the S plane, the system becomes unstable. So this contour is designed in such a way that it is covering the whole unstable half plane of the complex S plane. So this contour basically consists of the two portions. First is the imaginary axis, like this is J omega with omega varying from minus infinity to plus infinity. Then an arc of infinite radius that is covering the entire right half of the S plane. So this is the Nyquist plot. This is the Nyquist contour that is covering the entire right half S plane. That is the unstable portion. Then corresponding to this Nyquist contour in S plane, we draw a Nyquist plot in the J omega in the GSHS plane that constitutes the that is used to ascertain the stability of the system. So Nyquist theorem for stability states that for open loop transfer function, that is the number of poles of the open loop transfer function lying in the right half of the S plane, that is equal to 0. Because whenever we are having a closed loop type of the system, it will be having two transfer function. First is the open loop transfer function that will be given as GS multiplied by HS. Then we'll be having the closed loop transfer function that is given by GS divided by 1 plus GS HS. So in order to ascertain the open loop stability, we just take up the poles of the open loop transfer function. In case they are all the poles are lying in the left half of the S plane, the system will be open loop stable. But when the system is open loop stable, then it means that GSHS has no pole in the right half of the S plane. Then encirclement of GSHS contour corresponding to Nyquist path around the critical point minus 1 plus J0 must be 0. That means that GSHS contour should not encircle the critical point for the closed loop system to be stable. So we have already shown you the Nyquist contour. Corresponding to this Nyquist contour, we make up a Nyquist plot in the GSHS plane. If a system is open loop stable, then for the closed loop stability, this is the condition that net encirclement of the point minus 1 plus J0 by this Nyquist contour. This should be Nyquist plot. It should be 0. Then for the system to be, in order to ascertain the system stability, system closed loop stability for open loop unstable system, it means that there are certain poles of the open loop transfer function which are lying in the right half of the S plane. Then how do we ascertain that whether it will be closed loop stable or not? So in case the net encirclement of the Nyquist path around the point minus 1 plus J0 is equal to the total number of right half poles of the open loop transfer function, then the system will be closed loop stable. It means that it may be the case that the system is open loop stable. It may not be the closed loop stable. It may be the case that system is not open loop stable. It may be the closed loop stable. But how to establish that stability? That stability is ascertained with the help of the Nyquist theorem for stability. So this is GSHS is equal to 1 divided by S into S plus 1 into S plus 2. So in case we, this is the GSHS plane. Within this GSHS plane, if we want to draw the Nyquist plot, then it will be simply a polar plot. So this polar plot for 1 divided by S into S plus 1 plus S plus 2, it will be given by this omega starting from 0 to infinity. The polar plot will be taking this shape. Then this particular transfer function is having a pole at S equal to 0. So it is having a this one Nyquist contour will be having a singularity over here. So corresponding to that singularity, we get a curve of infinite radius over here. Then this polar plot or the Nyquist plot for omega equal to 0 to infinity, it will be having its image counterpart for omega equal to minus infinity to 0. That is shown over here. So when we complete the curve, this is the complete Nyquist plot for this particular function. And if we this is the GSHS. So in this case, we are having 3 open loop poles at S equal to 0, at S equal to minus 1, and at S equal to minus 2. So the system is open loop marginally stable because it is having non-repeated root at the origin. Then when we talk about the closed loop stability, then we can very well see that it is not having any root in the right half of the S-plane. So for the system to be closed loop stable, it is necessary that net encirclement of the Nyquist plot corresponding to this open loop transfer function, that should be 0. So if we just look at the shape of the Nyquist plot, it is just away from the point minus 1 plus j0. It is not at all encircling it. So the system is closed loop stable. Then another type of the question that we can do with the help of the Nyquist plot is shown in this example. The open loop transfer function of a control system is given by, this is GS is equal to this. We have to determine the value of K so that the system may be stable with gain margin equal to 6 dB, first case, then phase margin equal to 45 dB. In the first case, gain margin is given. Gain margin is basically the is the factor by which the gain can be increased so as to bring the system to the verge of instability. And mathematically, it is represented as 20 log of 1 by a to the base 10. So 20 log of 1 by a to the base 10. So gain margin is equal to 6 dB. So 6 is equal to 20 log of 1 divided by 4. So A is the point of intersection of the Nyquist plot on the negative real axis. This is equal to 4. So A is the point of intersection of this. So this is 6 is equal to 20 log of 1 divided by A. So when we solve this, A will be having a value equal to 0.501. So GS is equal to this. GJ omega will be equal to this. So we just take up the point of intersection on real axis. We equate the imaginary part as equal to 0. The value of omega is coming out to be equal to this. At this value of the omega, the magnitude is equal to this. And putting this value of magnitude in this is equal magnitude as equal to, this is equal to 0.501. So A will be equal to K will be equal to 122. So because we are taking it to the verge of instability. So gain margin is basically giving us the gain is simply giving us the factor by which the system gain can be increased so as to move it to the verge of instability. So here we have just got the value of A corresponding to the gain margin. And by using this value of A, we have just determined the value of K that will take the system to the verge of instability. Similarly, the second portion of the question is where phase margin is given, and corresponding to this phase margin, we get the value of frequency at this. Now, we just when we solve this equation, then we are getting two value of the frequency. First is the negative one, and second is the positive one. Considering the positive value of the angular frequency, we are getting omega is equal to this. So when we just put up the omega equal to 1.48, then the value of the K is coming out to be 37.22. So this is the value of K, so as to maintaining gain margin equal to phase margin equal to 45 degree. So this way we can design the system, we can get the value of the system gain for a particular value of the gain margin and the phase margin. Gain margin and phase margin are basically defining the relative stability of the system. In case both of them are positive and more is the value of the gain margin and phase margin, it means that more stable the system is, more it is away from the instability portion. So these are two specifications that help, frequency domain specification that help us to identify the relative stability of the system. And for particular value of the gain margin and phase margin, then we can very well see that we can get the value of the gain that should be fixed, so that we have derived over here within this example. So I hope that this lecture will be helpful to you all, and you will be able to do the question associated with the Nyquist plot after watching this particular video. Thank you so much.